Hi folks. Today we're going to basically finish out this section of chapter 7. I think it is. I'll not remember the number, but there's basically three famous theorems that kind of close out this section that I want to talk about. And then these are theorems that carry people's names, so that's always an indication that a thing is a little bit of a big deal if it's named after somebody. And in the midst of this, I'm going to try to pull in some connections to abstract algebra, because I know a bunch of you are taking abstract now. And this course actually is very related to it. The foundations of number theory and abstract kind of developed historically together, and then they sort of went their separate ways in the 19th century, 1800s. But, well, more like the 20th century, actually. Around 1900 and forward is when they sort of really diverged. Okay, so what are these theorems? The first is Lagrange's theorem about polynomials, about modular polynomials. There are actually several famous theorems that have this guy's name associated with them. Trying to think of his full name. I think it was Joseph. Well, it's French, right? So he probably pronounced it differently. But Lagrange was actually kind of famous as Napoleon's mathematician. He was one of the many. Well, there were several mathematicians that figured prominently in the French Revolution and became kind of favorites of Napoleon. After the Revolution, they had this commission to set up the metric system. They had a commission about weights and measures because they really didn't like the old stuff, which was all based on like the king. They were kind of sick of kings at that point. Like, that a foot literally was the length of the king's foot, and if the king changed, they changed all the feet. No, that's not quite true. Earlier in history they did. By the time the French Revolution came, they had standardized on a standard foot. But the yard was the distance from the tip of the king's nose to his extended finger. That's why they wanted to get things that were a little more sensible. They didn't do that great of a job on everything. They still stuck with the second, which we inherited from the ancient Babylonians. So that one's weird. Meters, kilograms, other units that are related to or that are derivative from the units for mass and length and things. So got created in that time. So they had mathematicians assisting them with them. That was one of the things. He was also famous for helping to establish a system of French schools in the parts of Africa that were administered by the French. Administered is the nice word for it these days. We'd probably call it French imperialist machinations. But anyway, Lagrange was a pretty big deal, and a lot of theorems named after him. I don't know why I just went off into this historical sideline. Lagrange's theorem for polynomials, or modular polynomials. That is, polynomials taking modulo something. And it's kind of a reassuring result. It tells you that polynomials work the same in modular arithmetic as they do in ordinary arithmetic, with one proviso. So let me write down the theorem and then you'll see. If f of x is a polynomial, actually we should say non-trivial polynomial, because I don't want f of x to be 0. If it was literally the number 0, then it doesn't really have any dependency on x, and so its value will always be 0. So for any x value, you'd get 0. And the point of Lagrange's theorem is we're going to count the solutions. So let's take out that kind of weak issue anyway. If f of x is a non-trivial polynomial, this word non-trivial in this case simply means it's not equal to the constant 0. With integer coefficients. Do you want that? And additionally, I'm going to talk about doing this in a mod system, but a particular mod system, mod P, where P is a prime. Whoops. Sorry. I skipped over a really important phrase in here that I meant to say. F of x is a non-trivial polynomial with integer coefficients, and we know what its degree is. Its degree is going to be d. Now the thing about the modulus, it's going to be, and p is a prime number. I guess I should say then, and tell you what we're going after. The roots, or zeros, of f of x in a mod p setting. So f of x congruent to 0 modulo p. Well, you know, if this wasn't mod p, if I had a degree d polynomial and we were just looking at f of x equals 0, how many solutions does that have? It's funny because it could range. You know, for instance, if this degree was even, you could have no solutions at all. If it's odd, you always have one. You know, I'm thinking about real things, so you can think about the graphs of polynomial equations. And if the degree is odd, it goes to minus infinity on one side and plus infinity on the other, maybe vice versa. But still, it's kind of crossed through the axis, the x-axis somewhere. So odd degree polynomials have one or more, and even degree polynomials have 0 or more solutions. But what's the upper limit on how many solutions you can have? It comes from the degree. You probably know this, that I don't have room to write this anywhere. Here's a little quick graph. That's a graph of a cubic polynomial. That's sort of the generic way they look. Cubic degree, you only have 3 solutions. You don't have to have 3. You might have something like this. That would be cubic, and only have 1 solution, 1, 0. But you could have at most 3. Well, that's the setting here too. If we're working mod p, a degree d polynomial is going to have at most d solutions. Of course, the solutions now would be congruence classes mod p, so not thinking about integers anymore, but the polynomial, you should probably be thinking about it as just being a polynomial. We don't really have to restrict it to being mod p. That is, you don't have to necessarily have coefficients that are reduced to mod p. They could be whatever. So it's only the degree of it that matters. That tells you what's the maximum number of solutions you could have. I'm not going to prove this one. I just want you to know about it because it's a bit of a reassurance, right? That you're not going to have more solutions than you would expect if you were dealing with real numbers. It's telling us that things work pretty much the same. It's an important proviso, though. It's only for prime moduli. The example we've already looked at was solutions to x squared minus 1 equals 0. So if I do x squared minus 1 congruent to 0, I don't know, how about mod 7? That's a prime number, right? You can see that this will have 2 solutions, exactly 2 solutions, because this is really the same thing as saying x squared is congruent to 1 mod 7. Just add 1 to both sides, yeah? And we just looked at that at the last lecture, that x squared congruent to 1 had 2 solutions, and they're basically 1 and minus 1. Now when we did this modulo something that wasn't a prime, we ran into this thing where there were a bunch of entries that were their own inverses, and where that meant their square was equal to 1. And so for non-prime moduli, you may have other things going on, but when it's prime, this is what happens. X squared congruent 1 only has 2 solutions. How many solutions would you think x cubed congruent to 1 would have? Mod 7. Well, Lagrange's theorem tells us at most 3. I actually don't know. Let's explore. Let's look into this a little bit. How many solutions do you think? Oh, I can't write that. How many solutions does x cubed congruent to 1 mod 7 have? Why did I put that extra parenthesis at the end? I don't know what my brain was just doing. What I really needed there was a question mark. There we go. It's not that hard to do, actually. I'm just going to need a little space to make a table, so I'm going to kill some of these words. That's bad of me, but that's the exploration. How many solutions does x cubed? Okay, we'll write the does in here so it doesn't look like an incomplete sentence. I just need to keep a record of what's the values of x and x cubed. Of course, everything done mod 7. 0, 1, 2, 3, 4, 5, and 6 are the possible values for x if we're working with reduced values mod 7. And the cubes are 0, 1, and oh, what's 2? 2 cubed is 8. Yeah, that's 1 mod 7. 3 cubed is 27. What's that mod 7? That's 6. Let me just work that out. 3 cubed, 27, minus 6 would be 21, and that's a multiple of 7. Yeah, so this is 6. 4 cubed is 64. Let's see, 56 is a nearby multiple of 7. Nope, 63 is an even better multiple of 7. Sorry. 64 is 1 more than 63. There's another one. Huh. Okay, so far we found 3. I'm saying now, because of Lagrange's theorem, I know the rest of these things will not be 1s. Because we've already got 3 solutions, and Lagrange's theorem tells us that that should be the max. 5 cubed, this is, oh gosh, 125, right? Let's see, that's 70 plus 55, that's 6. Really? 1, 1, 6, 1, 6, 1? That's just strange. No, this is going to be 6. I should clue you into my thinking a little bit here. This number, 6, in mod 7 arithmetic is -1. So I actually know what its cube is really quick. What's minus 1 cubed? Minus 1. So it's its own cube. That'll be a 6. That's a strange pattern in the cubes. 1, 1, 6, 1, 6, 6. Sort of a, I don't know, a reversal of the roles of 1 and 6 in the bottom versus the top. I'm not sure how to describe that. But look at the 3 places where we did get a 1. That's the point that Lagrange's theorem is supposed to tell us. As long as we're doing mod p for some prime p, we have a cap on the number of solutions to any polynomial. It's just as, check out what the degree of the polynomial is. So the next 2 theorems are due to Wilson, fairly modern result, and Fermat, a somewhat old result from like the early 1700s, no, late 1600s, I guess. Wilson's theorem and Fermat's theorem. But before we talk about them, I want to contextualize things a little bit, especially for those of you who are taking abstract. There's, I don't know what approach Dr. Damore is taking with this abstract class. Sometimes people do a rings first version. Other people do just group theory. But there's really 3 distinct kinds of algebraic structures that we study in algebra. And actually there's more beyond this, but the beginning courses usually have groups rings and fields. And there's another category before groups called monoids, and sometimes people talk about semi-groups, but they're sort of taking away structure from a group and saying, well, what if you didn't have all the structure that a group is supposed to have? I just want you to know these big three, and depending on the path that Dr. DeMoore is taking in abstract, this context may help you sort of pull things together a little bit. The big difference between these two things is groups have one operation, and that's it. So you'll have a set with a single operation involved. Rings and fields both have two operations. Normally, we write the operation in groups as if it was just multiplying. So usually just multiplication, although sometimes we'll write groups additively too, so usually a dot. But when there's two operations, it's a multiplying and an adding. Now, the difference between rings and fields is basically fields, named after me, by the way. No, fields play nice. In a field, you can solve equations. You've got the ability to do all the operations you want, that you need in order to solve equations. Rings, not so much. Sometimes you can't solve things in rings. You can solve certain problems, but not everything. And the basic difference is this. In a ring, you may not be able to divide. I'm saying it, you may not be able to divide, but a smarter way to say it is you may not have a multiplicative inverse for some elements. You actually will have additive inverses, so you can always subtract, but you may not be able to multiply by the inverse, and that's what really division is. And in a field, you will. At least you're never going to have a multiplicative inverse for zero, but everything besides zero, you'll have inverses. So the classic examples you should sort of keep in mind when you're thinking about these is the integers. Z is a ring. Because, if you have two integers, you can add them, right? So you've got the plus operation, and you can multiply them. So you've got the multiplication operation. There actually is more to it than this. For instance, you have to have the distributive property has to work out, right? There's a few axioms for being a ring. But the main thing is you've got to be able to multiply and you've got to be able to add, and they have to distribute. But you don't have multiplicative inverses for most things. In fact, the only elements of the integers that do have multiplicative inverses are 1 and -1. There's 2 is an integer, but 1/2, its multiplicative inverse just isn't. So Z is a ring. If you, instead of that, you work with fractions, now you have a field. And the idea here is every element of the rational numbers, except for 0, because you can never divide by 0, but for every number other than 0, you can find its multiplicative inverse. What is it, right? If you have a fraction a over b, its inverse is just b over a. And unless a were 0, and that would make this whole thing be 0, this is perfectly good as a rational number. So do you have inverses, multiplicative inverses for things? If yes, you're a field. If no, then you're only a ring. It's like a field with some of the goodness taken away. People actually use these things. I mean, after all, the integers is a useful algebraic system to work in. So I'm not saying that rings are bad, but that you don't have necessarily all the tools you might like to have at hand for solving problems. Multiplicative inverses are quite useful. Okay, let's talk about this last thing, groups, because the examples we're going to be seeing actually turn out to involve groups quite a bit, and I made a prop for this purpose. This is a piece of square. I don't know what this material is, but I was using it as insulation around my 3D printer, and my 3D printer's offline right now, so I scavenged it for you guys. So it's a roughly square piece of some kind of plasticky stuff, and I've labeled the front of it with the letter F for front, and I've also put numbers on the corners of it. If I flip it over, I wasn't clear whether you'd be able to see through the plastic because it's a little bit, it's translucent, but it's not completely clear. So I traced over everything on the back, but you can now tell that this has been reversed, right? The F looks backwards. So one nice example of a group is all the motions that you can do with an object like this. And there's quite a few. You can rotate it in place, and you can do that twice, or 3 times, or 4 times. But you know what? If you do it 4 times, you might as well have not done anything. Yeah. So that's an interesting observation, which I'm going to write down on the board here. If we've got a group, or if we've got that group, we have this one element, R. I'm going to call it R for rotate, right? R means rotate 90. Which way was I going? I think it was going clockwise from your perspective. And we just visually illustrated that R to the 4th is like, don't do anything. 1 is always what people use as the identity element of a group. But it's a little strange to think of 1 as this. I pick up this square and I don't do anything to it. That's what 1 is. Let's leave it alone. What would R inverse be? Does R there have a multiplicative inverse? Sure it does. Go backwards. And you may note that if you do the backwards turn 4 times, you come back to where you started. So R to the -4 is also 1. That leads to some interesting stuff because, for instance, you can split this R to the 4 up into 3 R's and another R. That product is 1. Oh, I didn't say this, but this is just putting parentheses around things, and groups have that rule. You're allowed to do reassociations. Well, that one's R cubed, and that one is R. And if R times R cubed is 1, that tells you something. R's inverse is actually this quantity. It's interesting that you can play these sort of games with R. R would be called a generator for the group I've been showing you. What we've just done right now is made a group with 4 elements in it. The group elements consist of rotating 90 degrees, or rotating 180 degrees, so 2 R's, or rotating 270 degrees, which is the same thing as rotating back 90 degrees. That's what we've just set there. And then not rotating any degrees. That's the 1. So that's a 4-element group, and it's quite abstract, and it means motions of something, symmetries of an object. There's a lot of groups that arise in that fashion, actually. That's one of the more interesting categories of groups, the symmetries of physical things. You can throw another wrench into this if you allow motions of this object that don't leave it facing forward. Like, for instance, I could grab it by these corners and flip it like that. Or I could grab it by these corners and flip it like that. And I just ended up turning it upside down, didn't I? Oh, that was cool. Let's try that again. It's right side up, flip it by this corner, then pick the other corners and flip it by them. Yeah, it ended up upside down. And facing you again. I had these 2 different flips, flip 1 and flip 2, and when we did them one after the other, it gave me R squared. This is the kind of games that you play with groups. I just wanted you to see an example of something where there's a single operation. Now, what is the operation when you're talking about a group? Well, in this case, it's composition of functions, really. These motions are actually functions where we think about the function means move all the points in the plane in a prescribed fashion. And if I follow one move all the points in the plane by some other move all the points in the plane, you've got something new that could be viewed as a sort of simultaneously do whatever it was that ended up, right? There's probably one last point I should make while we've got this prop in front of you, which is groups are the first place where we see non-commutativity rear its head. So let's see, I want to give you an example of something that does not commute. Let's look at the flip around the vertical axis. So it looks like that. Just takes you from the front view of the thing to the back view of the thing. 1 and 2 got interchanged, 3 and 4 got interchanged. If you do that flip twice, you're back where you started. So you know that flip squared is 1. But I want to combine flipping and rotating. So let's do flip first, then rotate 90. You see what position I'm in? The branches of the F point upward. Right? Let me bring us back to the start. Now let's do rotate and then flip. Well, we still are looking at the back side now, but see how the branches of the F are pointing downward, whereas before they were pointing upward? Let me just do that for you one more time. Flip, then rotate. The F strokes are pointing upward versus rotate, then flip. In both cases, I did the flip around the vertical axis. I had to re-grip the thing to do that, but you get different results. So that says, in this sort of algebraic approach we're talking about here, that if you do rotate first, then flip, it's not the same thing as if you flip first and then rotate. So that's interesting, right? The commutative law breaks down in a really simple proof. All right, we'll see another example of a group when we start chapter 8. We'll be looking at the group of integers modulo p. I guess the non-zero group of integers modulo p, the multiplicative group, not p. So it won't look like symmetries of things, and we won't have to use letters for stuff. We'll just use the congruence classes as our variables, or as our things that we're operating with. But that's coming up. Last thing we're going to get through in this chapter is first Wilson's theorem, and then Fermat's Little theorem. Excuse me. All right, so what's Wilson's theorem about? It says something kind of weird about the number p minus 1 factorialized. P minus 1 factorial reduced modulo p. And what it says is this, that number is always negative 1. It's actually p minus 1, I suppose. So let's do an example of this. How about if p was 5? That's a prime number. So then what we're talking about here is 4 factorial. 4 factorial is 4 times 3 times 2 times 1, right? And that is 24. And so do you notice that 4 factorial mod 5 is minus 1. That's 1 before a multiple of 5. I should have marked this as an example. Now let's do another example. How about p equals 7? I don't want it to get too big because factorials, they grow super fast, so we gotta watch out for that. Well, of course we could use Sage for this kind of thing too, but if we're doing p equals 7, then the number we're factorializing is 6. So what's 6 factorial? 6 times 5 times 4 times 3 times 2 times 1. I already know this much of it. The end there is 24, and this part of it is 30. So what I've got is 30 times 24. That's 720. Well, do you notice that 721 mod 7? That's 700, so a multiple of 7, and 21, a multiple of 7, so this is 0. So what's 720 mod 7? Yeah, that's what we thought it would. Well, it's what the theorem says. 6 factorial is congruent to minus 1 mod 7. So the number right before 721. All right, so this one is something I think we should prove. We should see the reasoning behind this, this idea that p minus 1 factorial will always come out to be minus 1 if you're working mod p. It really comes down to thinking about mod p arithmetic as a group. So let's make the standard picture. This is what if you encounter it earlier in classes, they call clock arithmetic. Well, I'm going to make a clock with 7 numbers on it, which is a little hard to do. That's pretty close to the right layout. So 0, 1, 2, 3, 4, 5, and 6. Let's put those as the values on a clock. But we're not going to involve 0 because 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, right? So those are the numbers we're multiplying. We don't need the 0. So 6 factorial is basically the product of all the numbers on the clock other than 0. And we don't want to multiply by 0 because that would zero out the whole thing. So that's good. And even if we took 0 as 0, it certainly would make it 0. But if we did 1, 2, 3, 4, 5, 6, 7, it would still be 0 once we did it, reduce things mod 7, because now the factorial would involve a 7. But this thing is sort of the biggest product you can make that isn't either actually 0 or a multiple of the clock size, multiple of our modulus. All right, so there's 2 different kinds of numbers that we're looking at here in this thing. 1 and 6 both have the property that they are their own inverses. So I'm going to connect the thing to its inverse. They're just on a little loop like that. 6 times 6 is 36, but that's 1 more than 35. So 6 squared is 1, or well, 6 is its own inverse. What's the inverse of 2? I feel like we may have done this before, but it's not hard to figure out. You think about what are some other numbers that are 1 mod 7. 8's the next thing that's 1 mod 7, and 8 is 2 times 4. Which tells you that these guys are inverses. And I guess it must be that 5 and 3 are either their own inverses or they're a pair of things that are inverses. How does that work out? Well, 5 times 3 is 15. And mod 7, that's 1. So yeah, these guys are a pair of things that are their own inverses. Is it possible that there was actually maybe, I said, okay, 5 and 3 could have been their own inverses. Could have been something like that. Is that conceivable? Well, no, it's not. Because if it was, Judy made this observation the last time. When a thing is its own inverse, it's also a solution of x squared congruent to 1. Mod 7 in this case. How many solutions does such a thing have? Well, that's what Lagrange's theorem told us. It has 2. And we already know what they are. So if you're working in mod p, and 7 is a prime, this jump doesn't happen. The only places where you get these loops where a thing is its own inverse are at 1 and at minus 1. Everybody else has some other number as its inverse, which is what we saw. 3 and 5 are inverses. Great. So with all that laid out, what let's just write this 6 factorial out. 6 factorial is 6 times, I just want to, well, okay, let's write it once the usual way. 6, 5, 4, 3, 2, 1. But it's also 6 times 3 times 5 times 2 times 4 times 1. I just wanted to do that so we could group these guys, because they're inverses. Yeah? So when we simplify that, what we've got is 6 times 1 times 1 times 1. All of the multiplying by 1 is kind of pointless. We get 6. And in Mod 7 arithmetic, 6 is negative 1. Just occurred to me they could have stated this as p minus 2 factorial is always 1, because these other things must multiply to be 1. It's kind of interesting. Don't know why I never thought of that before. Well, maybe I did. Sometimes you go in circles thinking about this stuff. And actually, that example, you always tell students that examples don't constitute proofs, but that example pretty much tells you how to proceed in getting a proof of this. You think about writing down the congruence classes, or writing down the product of p minus 1, p minus 2, all the way down to 2 and then 1. And all the stuff in there breaks up into pairs that are inverses. Well, they're modular inverses. Which means all that stuff in the middle, it just disappears. It's all a bunch of 1s. And you get p minus 1 and a 1, but you get p minus 1. But that's negative 1. This does, of course, depend on us working mod p, so that this idea of inverses mod p can be used. But yeah, that's the idea. So isn't that cool? You can factorialize a great big number, and there's no point, if you're doing modular arithmetic, there's no point in actually making the calculation. You're just going to get minus 1. Okay, almost there. Let's do the last theorem. This is due to Fermat. Fermat was most famous for his last theorem, which was finally proved after like 400 years of people trying on it. It was finally proved just in the late 1990s. I think the original, the guy who proved it was Andrew Wiles at Princeton, at the Institute for Advanced Study. And he made the original declaration that he'd got a proof of it back in like the early 90s. And it didn't quite work. So a lot of experts looked at it and said, wait a minute, you got a little problem with this piece of the argument. And he went back into his study for a few years, and he got help from a few other people, but basically it was his job. He was the main thrust behind it, and he finally came up with a valid proof a few years later. What he did, though, was so not anything that Fermat could have had in mind that it's well, it's remarkable. Wiles himself said, mine is a 21st century proof. It couldn't possibly have been the proof Fermat had in mind. And if you haven't heard this story, it's a kind of a cool one. After Fermat had died, his son was going through his stuff, and he came across this translation of a book by Diophantus. And we talked about Diophantus in this course earlier. Diophantus was looking at this equation, x squared plus y squared equals z squared. And Fermat looked at this, and in the margin of the book, he wrote, yeah, but if those 2's are replaced with any number 3 or higher, there's no integer solutions. And this one has integer solutions. And that's what Diophantus's work was all about, finding integer solutions to things. So a very early number theory kind of thing. Fermat said, well, except for trivial cases, like you could have 0 cubed plus 1 cubed equals 1 cubed. But other than those trivial cases, if the power is anything higher than 2, you'll have no solutions to that. That's not what got everybody excited, because Fermat had done a lot of good work over his life. He was actually an attorney, but he did a lot of math, and he was usually good. This note he wrote in the margin that said he had found a truly miraculous proof of this, but the margin was too small to contain it. That was really titillating. All these mathematicians for the next several centuries were like, I want to find that proof. And I think people still today are hoping to find the argument Fermat had in mind for that. Let's fix it up so it turns out it's enough to look at this when the power is a prime. So that has no solutions. I don't want to spend the time belaboring this, but I should add no non-trivial solutions. Because like I said, you could have, well, put zeros in for all of them, right? You could do that. But nothing beyond those kind of trivial cases. Yeah, weird. So that was his last theorem. That's what I was just describing as Fermat's last theorem. There's books and documentaries and stuff about this. It's worth looking into if you have some spare time. I have a very nice book by Simon Singh about this topic that I'd be happy to loan people if you have an interest. Yeah. Fermat's little theorem, unfortunately, has the same initials as what we're going to look at today. And it is about powers of numbers modulo p. So if p is a prime, and let's take a to be, let me just write an inequality. A is a positive number, but it's smaller than p. Then if you raise a to the p minus 1 power, you will always get 1. Again, in mod p arithmetic. So any number between 1 and p minus 1, when you raise it to p minus 1 power, you'll get 1. A little strange. Let's just check that out for a small p. How about p equals 7? The possible a's would be 1, and I would be raising 1 to the p minus 1. I'm sorry, I made it sound like there's 1, but there's more. 1, 2, 3, 4, 5, 6. But let's say 1 to the 7 power, that would be just 1. Nothing to do. 2 to the 7 power. Oh, darn it. 2 to this. I already need my calculator, don't I? I brought it today. 2 raised to the 7 power is 128. Okay, actually I could have done that one in my head. Is that really 1 mod 7? Well, if it is, take away 1, and we'll have something that's 0 mod 7. Let me divide 127 by 7. And, oh, sorry. I'm doing the wrong thing here. I'm not supposed to raise it to the 1 to the 7 power. What power am I supposed to have? I hope you guys were screaming at the screens as I was doing that. It was supposed to be raised to the p minus 1 power. So I want these to be 6 here. That doesn't change, but this one's that'll be 64. Oh, I recognize 63 is a multiple of 7. 63 is 7 times 9, so that's congruent to 1, sure. 3 to the 6. That I definitely can't do in my head. It's 729. Well, if that's right, if this result is right, then this should be 728 should be a multiple of 7. No, 728. Actually, I can just see how that's going to work out. Divide that by 7. You get 104. So, yeah, that's congruent to 1. I think I'm losing steam, but you get the idea. Let's jump to the end. Sure. I'm not going to figure out the 6th power of 6. But what I am going to do is take the 6th power of minus 1. The 6 is congruent to minus 1. And that's an even power of negative 1. So it's 1. Actually, that's kind of cool because we can do that with 5 too. That's the 6th power of minus 2. And minus 2, positive 2 we already knew was 1, so minus 2 will be 1, except it might have been negative, but it won't be because there's an even number of minus signs in that expression. So, geez, we're almost there. Maybe I should do no, I'm going to stop myself and not do more of that example. Because honestly, what we want to do is prove it, not just example ourselves to death. So the trick for proving this, it's, I think, a clever one they use in the book. I've seen another approach to this that's more almost calculus-based. It involves a method of finite differences, which, yeah, it's fun. But this argument is sort of, it's got what they call, well, I would call it beauty. It's got elegance. Elegance is the word people use in math. So, given a prime, P, and A, that satisfies, it's in the range we're talking about. One less than or equal to A less than P. So the biggest A can be is P minus 1. That's a weird looking P I just made. Okay. Consider the set of all multiples of A. So we're going to have A itself, and then twice A, 3 times A. I guess I shouldn't say all multiples of A, because I only want to go up to the P minus 1th multiple of A. Last one would be P minus 1 times A. So we're going to look at this product, or we're going to look at the product of all those numbers in 2 different ways, and see that in one way, by Wilson's theorem, we get, well, you'll see what we get. But the first way I'm going to look at it is just say, let's multiply all these things, all the elements of that set, and then just rearrange. So if we have A times 2A times 3A times times P minus 1A, I can pull all the A's out to the front. And how many of them are there? There's 1 for 1, 1 for 2, 1 for 3, 1 for each number from 1 to P minus 1. So there's P minus 1 A's. And what's left behind, once I factor out all those A's, is 1 times 2 times 3, all the way up to P minus 1. And according to Wilson's theorem, this is minus 1. So if I could figure out what this product should be some other way, then that would kind of finish it for us. So let's see if we can figure out what this product, we know what this value is, and that would tell us what this value is, but I just don't know what the value of the product of all these numbers is yet. But we'll get there. The main point I need to make to evaluate this guy, the product of all the numbers in this collection I've been dealing with, is to think about starting with the numbers 1, 2, 3 up to p minus 1 and see what happens when you multiply guys by a. When you sort of think of a as a transformation, it's going to move 1, 2, 3, etc. to a, 2a, 3a, etc. What does multiplying by a look like as a transformation? Well, I've got room for, I don't have room for the full word transformation, so I'll just write trans. And I want to show you this by example. A couple of examples, but I think this will bring it, it'll help you see what's going on. So I'm going to write down all the values mod p for p equals 7. P is equal to 7. And I'm going to do a is 2 for now. 0, 1, 2, 3, 4, 5, 6, 7. Let's just multiply everybody by 2 and see where they go. So I'm going to send 0, 1, 2, 3, 4, 5, 6, 7 to 0, 1, 2, 3, 4, 5, 6, 7, because all the computations will be done mod 7. Oh, well, wait, 0 times 2 is easy. 0 times anything is just 0. 1 times 2, 1 goes to 2. 2 times 2, oh, 2 goes to 4. 3 times 2, 3 goes to 6. Where's 4 times 2? 4 times 2 is 8, and mod 7, that's 1, so 4 goes back over here. 5 times 2 is 10, mod 7, that's 3. 6 times 2 is 12, mod 7, that is 12, it's 5. Oh, no, there we go, it goes there. And 7 times 2 is 14. Oh, wait, duh, I've already got 0, so I don't need 7s. Bad, my bad. Shouldn't have even been there. We're done. What you should notice is this, the action of multiplying by 2 just rearranged everybody. Well, it didn't rearrange everybody, 0 stayed put, but everybody else just kind of got scrambled. Let's try that again. Let's do it with a equals 3. 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. Multiplying things by 3, 8. 0 goes to 0. 1 is going to go to 3. 2 goes to 6, all the way down the end. 3 times 3 is 9, but that's mod 7, that's 2. 3 times 4 is 12, mod 7, that's 5. 3 times 5 is 15, that's 1. And, well, I guess 6 times 3 must be 4, is that right? 6 times 3 is 18, which is 4 greater than 14. That's a multiple of 7, so there you go. And again, you see how multiplying by 3 just kept 0 in place and everybody else got scrambled. Now, I don't want to prove this fact, but this is a fact. Multiplying by a number in modular arithmetic is just a permutation of the digits, mod p. Mod p. This actually works for mod p only, not in general prime, but general moduli. Okay. Yeah, I think you get collisions if you have a non-prime composite modulus, but when you have mod p, it's called the left regular action. We're just multiplying by the elements of the group itself on the elements of the group, and you turn the group into a permutation group on itself. those of you who are in abstract, if you started looking at permutations, this is where permutations reared their head, where people began looking at thinking of a group acting on itself by just rearranging the elements. So if you take it, if you believe what I've just shown you, two examples, and it's a little past our scope, but we can prove that. It means this, that the product we looked at, 1 times A times 2A, I should just say A times 2A times 3A times 4A times all the way up to P minus 1A. That product is just a rearrangement of 1 times 2 times, it's a permutation, actually, of 1 times 2 times 3 times 4 times times P minus 1 without the A's on it. And this one we know what it is. Right? That's, again, Wilson's theorem. So this is congruent to minus 1. So the upshot now is that minus 1 is that product, and it is congruent to A to the P minus 1 times P minus 1 factorial. And so that's A to the P minus 1 times minus 1 by Wilson's theorem. That's also by Wilson's theorem. But look at this overall. If minus 1 is equal to this thing times minus 1, what must that thing be? This guy has to be congruent to 1. So that's Fermat's little theorem. I'll mention just one quick thing about Fermat's little theorem, finally, and then we can be done with this section, which I'm excited to go into the next section, because that's where we really see a lot of nice connections with group theory and with fields. The groups are actually the multiplicative part of a field, the things we're going to be looking at. Well, two things, actually. One is that we've said that A to the P minus 1 power is congruent to 1 mod P. If you multiply both sides of that by A, you get A to the P power is congruent to A mod P. And that's a nice form of the thing too. I think, let's see, this version of it works even if A is 0, which is kind of the cool thing. 0 to the P power, of course, will be 0 and 0 there, so it works trivially. But if A is 0, this part does not work. So we need an extra hypothesis that A is not 0 for the top version. This other version has a slightly, well, a tiny bit bigger domain of applicability. So that's one thing. And the other thing is the use of Fermat's little theorem. I wonder if it would work for me to start abbreviating Fermat's little theorem with a little l there, and then F with a big L would be his last theorem. Anyway, just silly. One of the uses of this theorem is that partially it has a converse. So if you have some modulus n, and A is some number between 1 and n, so 0 less than A less than n. A is in that range from 1 to n minus 1, really. And A raised to the n minus 1 is congruent to 1 mod n. Then n is kind of mostly sort of likely to be a prime. If this works for all the A's in that range, n is called a pseudo-prime. Now let me just write it in words. So if every one of the numbers from 1 to n minus 1, you raise it to the n minus 1 power, and you get something that's 1 mod n, then n is a pseudoprime. Well, let me just say it this way. N is probably a prime. So you may think that's not such a big deal because, good grief, if we were actually using this for computation, I'm usually going to be raising some number to a giant power here. And it's worse than that. It's worse than what it sounds. What they actually use this idea for, the converse of FLT, which isn't true, by the way, but it's close. What they use it for is when n has maybe 100 digits in it. And so A could have 100 digits in it too, because it's bounded only by n. And so what we've got here is a 100-digit number raised to a 100-digit power. Now how the hell are you supposed to compute that and find out that it's 1 mod n? Well, it turns out in modular arithmetic, that's not hard. You can actually do that quickly. In fact, in microseconds. It's crazy to believe that, but it's true. So we can make that check for a bunch of A's. And if they all come out to give us 1 mod n, then pretty likely that we've got a prime. And the discovery of very large multi-100-digit numbers that are primes is useful for doing cryptography. So it's kind of a big deal that we have this sort of a test. A test that we now use in internet commerce and crypto systems that goes back to this guy from the 1600s. Okay, so that's where we'll put an end to it for today. This video is coming out rather late. I apologize for that.